Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, let's do this. Let's do the Python part for module number 7, deep sequence modeling. So let's go to the folder, lectures and codes, and deep sequence modeling. And as you can see, there are three Python notebooks. One is for Univariate, the other one is for Multivariate, and there is another one for Intuition. So I'm going to start with the Intuition one, and then we go to the Univariate. Then in a separate video, we'll cover the Multivariate. Okay, so let's go ahead and open the Intuition one. So you can run it on Google Colab, but I'm going to go ahead and run it on my local computer because I already have GPU on my computer. So here it is. These are the three files that we're going to go over: Intuition, Univariate, and Multivariate. So starting with the Intuition. So let me go ahead and connect my environment for the GPU. So yeah, this should be it. And let's check the version of the TensorFlow. It should be 2.17. Yeah, there you go. All right, so we're going to import the packages. So the data set that we're going to work with is our airline passenger data. So we have seen these things before, so I'm going to go over it quickly. So the test period is 12, and then the rest is going to be the train set. So basically, this is what we're going to have, right? 132 observations in the train set and 12 observations in the test set. All right, so as we talked about it in the machine learning part, when we go over the Python part and machine learning section of the course, we need to create these booleans for train and test. We need these booleans for visualization down the road. So I'm going to save our passengers in something called series. And this is basically, now let's go ahead and prepare our data set for supervised machine learning task, right? So we're going to use 12 features. And then I'm going to start with the DNN model, right? So with a deep neural network, we already saw that we are treating each of those lag variables as features. So that's why here I'm going to have 12 lags, and the 12 lags are going to be considered as features. Then we're going to make, this is single output prediction, right? So we're going to use this for one step ahead or multi-step ahead predictions. For the multi-output, we're going to change this CY to, for example, 12 or 24 or whatever we want, right? So we already know how this thing works. Basically, if you want to look at the shape of the data set, so for X train, we have 120 observations with 12 features. Y train, 120 observation with only one target variable. And for the test set, this should make sense as well. All right, let's go ahead and run our, again, this is the Intuition file. I want you to see what is the difference between DNN and RNN at a high level. In DNN, we are treating all those lag variables specifically as features. In RNN, we're processing the data sequentially. So make sure you watch the theory lecture if this doesn't make sense, right? But basically, this is us going through the code, reinforcing what we learned from the theory lecture, and specifically when we talked about the differences between DNN and RNN. All right, so we're going to put together our DNN. This is a very simple network, with basically a couple of dense layers. With the first hidden layer has 32 nodes, the second one has 16, so the activation is ReLU. And we're going to add a dense layer at the very end with activation linear, obviously, because we're doing regression. And yeah, we're going to optimize over mean squared error, and we're going to use Atom Optimizer. All right, so we can look into the architecture of our model, and hopefully this should make perfect sense. For example, how we get these number of parameters, right? We're going from 12 features to 32 nodes. So 12 multiplied 32 plus 32 bias terms. So this is how we get 416. So 12 multiplied 32 plus 32, right? And the same story for this number. We go from 32 to 16 and then plus a 16. So that's how we get 527. And for the last layer, you can do the math, right? All right, so we can go ahead and train this. So this should be fast. We're running on 100 epochs, batch size 16, and obviously we're gonna, the validation set is gonna be the test set. So let's see what we get. And we can look at the history. So this is our validation loss versus train loss. And yeah, so this was our DNN, right? We can go ahead and use that DNN, deep neural network, or artificial neural network for making predictions, one step ahead or multi-step ahead, right? We have seen these things before. We just need to make sure that, the first TX variables are not, the TX observations are not predictable, right? Because we use 12 lags. If I use 12 lags, I cannot predict them. And then we can go ahead and use model.predict. So this is going to give us one step ahead, right? When I do one model.predict. So we can look at the predictions in the train set and the test set. We can add it to our data frame. So these are the predictions in the train set and the test set, right? We can visualize it. And as you can see, our network is doing an okay job, both in the train and test set. We know that we can do a lot better using simple econometrics or machine learning models. But again, remember guys, this is a very simple deep neural network using 12 lags. It is doing okay, but obviously for a well-behaved data set like this, we didn't need to use deep learning. Okay. All right, now the next one, we're going to talk about RNN, recurrent neural network, right? So instead of thinking of those 12 lags as specific features, we're going to train the model sequentially using some sequence lengths, for example, 12 here, right? So the number of features is going to be 1. So the time series itself is your only feature, and we're going to process the data in a sequential manner. So the sequence length here is 12. So this is, if you remember from the theory lecture, this thing, the sequence length, is going to be the length of your memory, right? Either in RNN or LSTM, we talked about this concept of memory, right? So in RNN, we have this kind of shorter term memory, and that memory is coming from the sequence length. This is the length of the memory. And then how many recurrent cells we're using in our network, that's going to be the depth of our memory, right? So for example, here, the length of our memory is going to be 12. So we're processing the data in a sequence of 12s, right? So this is it. We can go ahead again. I'm preparing the data and to pass it to an RNN. So here's a little difference between RNN and DNN. We need to reshape the data set. In this way, I'm going to show you the output, and it should make more sense. Because remember, your RNN is processing the data sequentially, right? So for example, our X shape looks like, we can look at the shape of train and test set and talk over that one. Look at that. The shape of the train set is 120, 12, 1, right? This 1 stands for feature. 120 is the number of observations sampled, and this 12 is your sequence length, right? So we are processing 120 of these sequence length of 12 with one feature. So this is your X train. And obviously for your Y train, there are 120 of those targets. The same story for your test set. So hopefully you can see the difference between this one, the data that we pass to our recurrent neural network, versus this one, the one that we use to pass to our deep neural network, right? So here, 120 observations, 12 features, specifically each lag is a feature. Here in RNN, there's only one feature. This is feature, and this is the way that we pass the data to an RNN in a sequence. So 12 sequence and then 120 observations, right? Then the rest is pretty straightforward. So we're going to say, okay, our optimizer is Atom. So I needed to change the learning rate to make sure that it converges faster. And what do we have? So look at that. This is just pretty much the same as our DNN. I create my function, build RNN model. And what are the inputs? The sequence length and number of features. So these are, in RNN, there are two numbers that matters a lot. One is the sequence length, the length of the sequence that the model is going to process the data, and how many basically recurrent cells you use in the network. So I want you to think of this one as a length of your memory and this one as a depth of your memory, right? So if I only have one, let's say, recurrent cell here, one recurrent layer like what we have here, simple RNN. So this network is not too deep when it comes to the depth of the memory, even though the sequence length is 12, and whatever it is, if it is 12, 24, 48, whatever it is, the depth is not that rich, right? So we can go ahead and stack a bunch of other RNNs on top of this one to make sure that your memory is deep enough as well, right? But again, here, this is the intuition file. We're going to keep things simple. So this is the simplest network you can think of, simplest RNN you can think of. We have input. We have a simple RNN on top of that with 16 recurrent cells. And I'm going to say return sequence is equal to false because we're going to do many to one, right? And then, yeah, activation linear for the dense layer, and that's it. So let's go ahead and create this one. We can go ahead and build it, look at the summary, and hopefully you remember how we can calculate this number 288, right? Remember how many features we had? 1. We're going from 1 feature to 16 of these recurrent cells, so 1 multiplies 16. And from each of these recurrent cells, 1 hidden state to another hidden state, so we go from 16 to 16, so 16 multiplies 16, and then we're going to have 16 bias terms. So that's where this number 288 is coming from. Again, if this is too fast, just make sure you watch our theory lecture when we talked about these numbers in details. All right, so this should run fast as well. So I'm going to go ahead and run it. We're going to train this RNN and see what's going on. So now our RNN is being trained, and we want to go ahead and look at 1 step ahead forecast, right? So again, we have seen this before. Let's set a placeholder. So these are, I'm going to use model.predict to just use 1 step ahead forecast, and let's add it to the data frame. So remember, I'm adding it to the data frame that we already had DNN forecast as well. So DNN in the train, DNN in the test, now RNN in the train and RNN in the test, right? So we can visualize it, and then boom, there you go. So you might wonder, and I'm only visualizing the RNN here. The DNN was doing a decent job, so now RNN. And you say, wait a second, what's going on here, right? Because is your RNN missing something? And the answer is absolutely yes. We are not picking up any trend or seasonality. Basically, it's giving something close to average. What's going on here, right? And obviously, I can go ahead and compare the performance of the model. We don't need to do that. RNN is unbelievably underperforming DNN. But what does that mean? Should we give up on RNN? What's going on, right? So let's look at those. Again, this is the intuition file. I want you to just be aware of what are we doing here. If I look at mean absolute percentage error for the DNN, it was only 2.8%. But for our RNN is 41%. Again, no wonder. I want you to compare this one with actually the one that we had at the top, which was this one. Obviously, the RNN is underperforming by a huge margin, right? So I want you to pause the video and think about it. What is going on here? Why the RNN is missing? Well, basically, you can think of why RNN is failing. So pause the video and think about it. Okay, I went ahead and increased the font size for better visibility and hope it looks better now. So what is going on? Is RNN failing? Just remember, it seems that our DNN is able to work on a plain vanilla version of the data. This data is basically non-stationary. There's a clear trend and seasonality, and we didn't do any kind of transformation. So on the raw data, the DNN is working, but RNN is not working. So what's going on? So here at a high level, this is what's going on. So when we are modeling our time series using DNN, basically, if I use, for example, 12 lags, we are using those 12 lags as independent features. So we're specifically adding those lags as features to the model. So that independent features is going to basically capture trend and seasonality without necessarily understanding the sequential data, right? So just think of it as a simple linear regression model. So if I have a simple linear regression model, and if I simply say your y variable here, airline passenger, is equal to b, a constant term, plus w1 lag 1, w2 lag 2, w3 lag 3, all the way to w12 lag 12, this simple linear regression model is probably able to capture that kind of behavior in the non-stationary data set, right? Even without understanding the sequential relationship, the temporal relationship in the data, simply because this data set was very well behaved. And even including one or a couple of lag terms in a linear regression model is going to do a decent job in the train set. So, and this is exactly what's going on with your deep neural network, right? After all, if I use linear activation function with one layer, what is DNN? DNN is simply my simple linear regression model, right? So, however, in RNN, so that's why even without pre-processing the data, the DNN was able to perform okay on the non-stationary data. However, for RNN, it's because the data is being processed sequentially, that sequential processing can capture temporal dependencies, but we'll struggle with non-stationary data set, right? So that's why we need to make your data set stationary. We need to pre-process the data and take for example, we can take difference and things like that to help basically reveal the pattern by stabilizing the mean and variance, especially if you want to do longer term predictions, right? So in this data set, simply because it was well behaved, our DNN worked just fine. But if it was on the levels, and RNN was having hard time because those 12 lags was not specifically modeled as features. So that's why your RNN is not performing good here. But you're going to see that down the road, later in this notebook, when I go ahead and pre-process the data, basically I can do log transformation and I can take the difference, work with the stationary data. You will see that the RNN is going to shine, right? So let's do that. So let's go ahead and pre-process the data. We're going to go ahead and create this new data frame called data transformed. And then, as I said, I'm going to do the log transformation first and take the difference of those logs, right? So we can visualize it. So this is what the time series is going to look like. And we're going to apply RNN, the very same model, the very same RNN architecture, now to this data set instead of the levels of airline passenger. And let's see how it performs, right? So we're going to drop the NAs. And again, the rest is pretty much exactly the same as what we did in the RNN, apply to a level data. So we have seen all this before. Let's run it. And we have one observation less because we're taking the difference. So that's why it's not 132, it's 131. And this is 119 instead of 120. All right, so again, the model is pretty much the same. We have seen this before. So let's go ahead and build it again. The number of parameters and everything is going to be the same. Now I'm going to train it. Train time is basically the same. And let's look at, as you can see, this looks a lot better now compared to what we had for RNN applied to a level data set, right? So I can go ahead and make one step ahead predictions just like before. So remember, we're going to make predictions on difference log passengers, right? So these are your predictions. You need to convert them back to levels, right? So what does it mean? It means that you have to undifference them first and then make it to the exponential, right? Because you took the log first. Now, if you want to reverse it back, so you have to do e to the power of something. So now we can go ahead and make prediction in the train and test set, obviously. So these are the predictions in the train and test. We can add it to the data frame. And then this is the part that I was talking about, right? So first, I'm going to go ahead and undifference it. So we created this, we're going to create this shift log passenger. This is just one lag, right? And then we're going to add it to these deltas. And then to exponentiate it, right? So this is what we're doing. So we're saying that e to the power of that thing, the previous log passenger plus the difference that we predicted, and then e to the power of that thing, right? So we are again, as I said, we are adding back this, we are undifferencing it first, and then we do e to the power of that thing to just to unlog it, right? So if we do this one, we can look at the data set. So remember, this was your diff log passengers, and we made prediction for these ones. So this is in the train set, that's why you're not seeing it. And then we can visualize it like this as well. Okay, so as you can see, this looks a lot better compared to applying RNN to airline passenger levels, right? So we're applying RNN to difference of log airline passengers, and then we make predictions and we transform them back to levels. So this looks a lot better. Now we can compare the three models we have. You know, we have DNN, which use 12 lags as features, so 2.8% mean absolute percentage error. Then we have RNN applied to raw non-stationary data, which was obviously very bad, 41%. And now we are applying RNN to transformed stationary airline passenger data, which we get 3.6, right? So in this specific example, our RNN was not complex enough, and a simple DNN performed a better job. So 2.8% versus 3.6. But we know that RNN is designed for handling time series. And the reason that here it didn't perform better than DNN was two things. First of all, your dataset is super simple. It's very well behaved. We didn't need to do deep learning at all. We could use simple, for example, linear regression model or ARIMA or ETS. We know that ETS is gonna shine on this dataset, right? The second reason is that your RNN probably is not deep enough, right? So we talked about this depth of the memory and length of the memory. So maybe we need to stack a bunch of those RNN on top of each other. And then after that, we need to regularize the network or make it more complex to capture those temporal information better. And this is exactly what we're going to do in the next notebook. All right, now let's look into our second notebook. So let me pull up my browser. Again, we talked about intuition. We know what is the difference between DNN and RNN, how differently they are treating your time series. One of them is looking at lags as independent features. The other one is processing the data sequentially, and there's a big difference between the two. And now we know why RNN requires your dataset to be stationary or pre-processed. And we know that it's going to perform a lot better on a pre-processed dataset. Okay, so with that information, let's go ahead and open the Univariate one. So this is, again, I'm going to run it on my local computer, but I just wanted to show you how it looks like here and what's the plan. So we are going to work with our, again, airline passenger dataset, but this is going to be a lot more involved. We're going to talk about simple RNN, LSTM. We're going to make it more complex, stacking a bunch of those LSTM models on top of each other. We look into bidirectional RNN. And basically, we're going to see how we can do recurrent neural network or LSTM using TensorFlow in Python, right? And yeah, so let's go ahead and do that. And then after that, we are going to talk about the multivariate. So this is going to be the univariate one. Then in the next notebook, we're going to talk about the multivariate. So let's start with this. So I'm going to go ahead and open my VS Code again. So let me just go ahead and close this because we don't need it anymore. So this is the univariate, right? All right. So again, let's go ahead and connect to my GPU, TensorFlow 2.17. So we're importing the same data set, airline passengers, make sure that the index is correct so we can visualize it. We're going to go ahead and split the data. Again, guys, this is a general notebook for you guys if you want to do univariate time series forecasting using TensorFlow. Okay, so in this example, we have the length is 144. So we can go ahead and make a train, test, and validation set. I would say 60% train set, 20% validation, and then the rest is test set, right? So in this example, we're going to work with 86 observation train, 28 for validation, and 30 for test, okay? All right, so we know that the dataset is not a stationary, and in the intuition notebook, we talked about it, why we have to make it a stationary for RNN. So let's go ahead and do that. So I will take the log transformation first, and after that, I'm going to work with the difference log, right? So this is going to be the data set we need to work with. All right, so this is exactly the same that we saw in the intuition folder. So the difference between this one and the intuition notebook is that this one is going to be a lot more extensive when it comes to building RNN networks. And we're going to do multiple step ahead and multiple output forecasts as well. So in the previous notebook, we just saw one step ahead forecast. All right, so this is our variable of interest, diff log passengers, right? And it's obviously stationary. Okay, so do we need to normalize the data? In this case, no, because look at the scale and look at your time series, you don't need to do that. But in the next notebook, you will see that for temperature data set, we want to normalize it. So if you want to normalize it, you can go ahead and use this part of the code, but obviously we are taking the mean out and divided by standard deviation. There's nothing fancy here. And yeah, so let's go ahead and talk about how we prepare the time series to be passed to a recurrent neural network correctly in a TensorFlow. Okay, so we are going to work with something called time series dataset from array. So what is this? What is this time series batch generator and why do we need it? So remember guys, this is deep learning, right? And if you remember from the theory lectures, when we were talking about sequential modelings, we have to process the data sequentially, right? Your input is a sequence of time series. So we need to create those time series sequences first. So here is a simple example, and I want to work with a very simple series. Basically, this is a NumPy range between 1 and 9, right? And I want to show you how does this time series data set from array work. And here's the documentation. You can click on it. And basically, this is everything inside that module that you need, right? So time series data set from array. So you have a data, you have target, you have sequence length, you have sequence stride, sampling rate, batch size, shuffle, and etc., etc. So we're going to talk about all of them in this simple example. So let's see what we have. Again, we're going to say your integer sequence is this, a simple sequence between 1 and 9. And I want to create bunch of batches of time series or sequences from this sequence, right? From numbers 1 to 9, I want to create some batches of data. And look at the output, for example, 1, 2, 3. So this is going to be my X, and this is going to be, this is the sequence, and this is the target value, right? 2, 3, 4, 5. 3, 4, 5, 6. So I want to process the data like this. I want to pass something to my network, and this is a prediction. Well, this is a target variable. Pass something like this. This is a target. Pass something like this. This is a target, right? So let's see how it's generated. So what are the parameters we need? The batch size, we can go start with 1, but later on we're going to see, if you have enough observations, you know that the deep learning, the model is being trained better if we work with larger batches of data, right? Maybe 32, 16, and things like that. Then we have our sequence length. In this example, I want to work with a sequence length of 3. So basically pick 3 of them, make a prediction, pick 3 of them, make a prediction, and etc. And then H is the number of H step ahead for forecasting, right? So for example, if I say H is equal to 3, it's going to make a predictions from 3 steps ahead into the future, right? So you're gonna see the examples better when I change those numbers. And there's this delay thing. This is very straightforward. So this is a number of delayed time steps to start prediction, right? So for example, if my sequence length is 3 and I want to start from 1 step ahead, H is equal to 1. So it's 3 plus 1 minus 1. So it's going to be 3, right? So basically the delay is going to be 3. And then I'm going to go ahead and create this dummy data set using time series data set from array, right? So what does it do? So again, this is one utility from Keras and says, give me the data. The data is this, 1 to 9. And obviously I will go ahead and take the last delay numbers because my targets are going to start from delay all the way to the end. So I want to say the original data you want to use is from observation number 1 all the way to, I think delay here was 3, all the way to the last 3 observations, right? So exclude these things for the data, and your target is going to be starting from that delay onward, right? So then what else do we have? Sequence length, we decided to go with 3, and sequence stride. This is a number of time steps between 2 consecutive outputs. So I'm going to play around with it and see what happens. And obviously batch size here is 1. Shuffle, if you want to shuffle these observations or not. So here we're going to go with false. So this is going to be a tuple at the end of the day. Again, we call it dummy data set. So we created using this time series data set from array, and there are 2 things inside it, inputs and targets. I can go ahead and print input and target. I can go ahead and print the shape of that as well. So let's go ahead and run this and play around with these numbers. And so for example, if I go ahead and change the sequence length to 5, and then what do we get? It goes from, well, it's not enough data here. I can go to 20. There you go. So 1, 2, 3, 4, 5, and then 6, right? 2, 3, 4, 5, 6, and then 7. So we are not shuffling. Because we're not shuffling, these are all in sequence, right? If I go ahead and change it to true, obviously it's going to shuffle the data, right? Again, it's shuffled between observation. Within each observation, obviously your sequence is respecting the temporal information. So that's why in RNN, even if you're shuffling the observations, you might say that, okay, are we shuffling the time series? The answer is yes and no. Yes, you're shuffling observations, but you're not that much worried because the data is going to be processed in a sequential manner. And if your sequence length can be 12, can be 24, right? So hopefully you're getting the idea. I can go ahead and put it back to false. And then I can say, for example, let's play around with other stuff. So batch size. So for example, the batch size is 3. Then see what happens. You see, now I have 3 batches of data. So 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. And then what are the targets? Targets are going to be 6, 7, 8, right? 6, 7, 8. All right. So that's the batch of data. Let's go ahead and put it back to 1. What else do we have? So we talked about sequence length, batch size. Oh, H. So for example, imagine this H is equal to 5. What will happen? So 1, 2, 3, 4, 5, and then H steps from that. So it's going to be 10. You see? And then, for example, 6, 7, 8, 9, 10, H step from that 15. So this is what you want to make prediction for, right? So now we know H as well. What else? The last thing is a stride, right? So we can talk about the stride. So if I change this stride to 5, right? So as you can see, this is the number of time steps between 2 consecutive output sequence, right? So for example, 1, 2, 3, 4, 5, and then there are 5. Let me actually put it back to 2. You can follow better. So you see 1, 2, 3, 4, 5, and then there are two time steps between the 2 concepts. So it's going to skip 1 and 2, start from 3. This one is going to skip 3 and 4, start from 5. Skipping 5 and 6, start from 7. Skipping 7 and 8, start from 9. Okay, so hopefully now you have a clear idea of how this time series data from array is going to work, right? Why do we need it? Because remember, we had 143 observations, and this was the shape of our train sample size, validation, and test sample size. And now we're going to create 3 data sets using time series data set from array. And this is very straightforward, guys. Just pay attention. The series is going to be your difference log passengers. The sequence length is 12. Remember, we have 1 feature. The sequence length is different from how many features you have. In this example, we have only 1 feature. And then we are going to predict, from 1, if this is monthly data, 1 month from into the future, right? And then the delay is going to be 12 plus 1 minus 1, so it's going to be 12. And then batch size 32, right? So again, I'm going to go ahead and create 3 data sets: train, validation, test. Because when you're building your recurrent neural network, you train it on the train sets, you basically optimize the hyperparameters in the validation sets, and look at the performance of the model in the test set. Okay, so they are pretty much the same. So data, again, series, we're excluding the last delayed observations. Your targets are starting from the delay all the way to the end. Sequence length, we're not shuffling. The batch size is 32. A start index and end index. So this is train set starting from 0, ending number of train samples, right? Which is 86. For validation set, pretty much everything is the same except start and end. We're gonna start from the last observation in the train set all the way to the last observation in the, again, this is index in the validation, right? So it goes from 86, starting from 87, all the way to 87 plus 28, right? And then obviously the last one, the test set, is going to start from, your start index is going to be from 86 plus 28 all the way to the end. So that's why we don't have an end index here. Okay, so we can go ahead and run this cell. Now your data set is prepared, and we can go ahead and look at, for example, one of them. I can put a break here or not, it really doesn't matter. This is this first one, right? So now the data, look at that. This is processed in batches of size 32. The sequence length is 12, right? So I'm gonna have, for example, this is one sequence. I'm gonna have 32 of them, And these are the x's, and my targets are going to be somewhere here. Actually, let me show you some of those. So this is, remember, this is our time series itself. And I want to show the time series in the test set, right? So that's why I'm looking at the location from train samples plus validation samples all the way to the end. So this is my test set, right? And because I'm not shuffling, I should be able to track them. So look at that. We are not shuffling things. So look at that. This is, I'm looking at the first 12 observations. So this is the sequence 1, right? And then let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these are the 12 observations. And then I'm going to use this one as my X and then make a prediction for this, right? So this is my sequence number 1, starting from 0.028 all the way to 0.14. Let's see if that's the case. Yes, 0.028 all the way to 0.14. And what is the target value? The target value is this. 0.019. Is it the case? Yes, 0.019. So that's your sequence number 1. Then sequence number 2 starts from here. Sequence number 3 starts from here. Okay, so that's exactly what we're seeing, right? Sequence number 2, sequence number 3, sequence number 4, and etc., etc. And your target is going to be start from this one, and then this one, this one, this one. Let's see if that's the case. 0.019 minus 0.18. So let's see, 0.19 minus 0.18. Yeah, there you go. So this is, hopefully you get an idea of why we did this, right? Remember guys, in machine learning econometrics, we just use this time step and then use 12 lags, make a prediction for the next step. In RNN, we're doing things differently. I hope that you're realizing what's the difference. We are processing the data in sequence, so that's why we needed to create these sequences from this time series data set from array function. Okay, and the rest is honestly pretty straightforward. I can go ahead and show you the shape of your, for example, the train data set. In the train set, we have 32 of those sequences of length 12. Okay. All right, so then we can go ahead and start looking at the performance of our model compared to a benchmark, right? So our benchmark, let me show you what we're doing, what we're going to do. Our benchmark is simply a naive forecaster, right? So naive forecaster, let's go ahead and create that benchmark, naive forecaster. Okay, we need to go ahead and create this function called evaluate naive method. And guys, remember, what is your naive forecaster? Naive forecaster is the last value observed in the sequence, right? And whatever happens today is your best prediction for tomorrow, right? But before looking inside this function, I want to show you what's going on, basically by keeping track of sample scene and total absolute error. Well, basically the predictions. So let me actually show you what we have here. From this test data set that we created up there, we can look at the shape of it, shape of inputs and targets. So as you can see, the shape of input is, let's see, yeah, it is a 6 by 12 tensor, right? So 6 by 12, why 6, why not 32? Because guys, we said that there are going to be 32 batches, but remember in the very last, how many observations we had in the test set? It was, and how many was that? Yeah, it was 30, right? So out of these 30, obviously we cannot go ahead and create 32 batches. There's not enough data, but we can create 6 batches of data, which each batch has a sequence of 12. So that's why this is not 32. This is only 6. Okay. Yeah, there you go. And what I'm creating here says that, okay, for those inputs and targets in the test set, go ahead and create the predictions. Predictions are what? It says from your input, the last observation, all the rows and the last column. No, it's not working. Okay, we're going to go ahead and create this evaluate naive method, which basically is going to say, remember, what is a naive forecast? Naive forecast is the last value observed in the sequence, right? And we want to calculate mean absolute error for that thing, right? So this is the idea. We're going to look at the mean absolute error. But before looking at this, I just wanted to show you what is happening inside this, right? So look at that. We say, for example, let's look at our test data set, look at the shape. Our test data set is something like this. The input shape is a 6x12, so we have 6 batches of data. Why is it not 32? Because remember, our test set has only 30 observations, so we cannot create 32 batches of length 12. So with that, obviously we can only do 6 of them. So 6 of those batches length 12. So this is our test set, right? So this is what we already saw that. This is batch number 1, batch number 2, batch number 3, all the way to batch number 6. And these are your targets. The target is going to be something like this, 6x1, right? So we have only 6 of those numbers, 6x1. Okay, so then we're going to say, let's, for example, look at the predictions. So before me running this, let me show you the first batch in the test set. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is your target, right? What is the best prediction? What is the naive forecaster for this number? It's this number, right? So the last observation, so for example, this is the last observation in airline passenger data set, and then you're going to use it as the best predictor for this, right? So you know that already this is going to be the value of your first prediction, right? So that's exactly what we're seeing here, right? So for the first batch, this is the best predictor. For the second batch, this is the best predictor. These are simply lag values, and that's how we're capturing it, the lag value, right? From your input, give me the last observation. From your input, give me the last observation. This is going to be the prediction that want to step into the future. Okay, so, and now inside that function, we're creating this prediction. We're looking at how many samples that have been seen in that input, in that data set. In this example, it was 6. So we say, okay, let's calculate mean absolute error. Calculate the errors, sum them, and then take the average and report it, right? So this is what we're doing. So inside this evaluate naive method, I'm creating total absolute error, sample scene, and then from a data set, we're going to pass something to that. It can be train, test, validation, right? Predictions are your naive forecasters. Total observation, simply, this is total absolute error, right? It's going to say calculate the error, sum them. This is going to be your total absolute error, and then divided by number of samples seen. So this is going to be your mean absolute error. Hopefully this function makes more sense now. Now I can apply that function to the train set, test set, validation, and this is it. This is our benchmark, right? So the benchmark naive forecaster in the train set is 11, in the test set is 0.12. And now we want to see if our RNN is able to outbid this thing or not, right? Let me actually open the, let's see if I can have it. Yeah, there you go. This is what we're doing. And let's start with the simple RNN. So we're going to do simple RNN, then LSTM, then we are going to make it more complex, bidirectional RNN, and then that's it. We're going to compare them. So let's do with the simple RNN. The sequence length is 12, number of features is 1, and then this is going to be our first model. I can go ahead and put it in a, let's say I can go ahead and put it in a function, which we're going to do later. But here I want to explain one more thing before we move forward. So look at that, there's an input layer, there's a simple RNN in between, and then there's a dense layer at the end, right? So, and we already talked about how we can calculate these numbers. But what happens, for example, if I go ahead and change this return sequence is equal to true? This is what I want you to see before moving forward. So if I change it to true, if you remember from the theory lecture, this means that the output, each recurrent layer is going to output all the sequence as well. So this is going to be many to many instead of many to one, right? So this layer is going to generate something many to many. So if I run this, pay attention to the shape of the recurrent layer. So it's not going to be non-16. So it's going to create those 12 numbers, because remember your sequence length is 12. On top of that, right? So if I run this, see what happens to this. There you go. So it's 12 and 16 now, right? So because, again, if you're doing many to one, if you set it equal to false, if you're doing many-to-many, or if you want to make your network more complex, so for example, I want to add another layer on top of this, right, with 32. If I want to do something like this, I have to make sure that this is true, because what this network is expecting is in shape of sequence length of 12, right? So I have to do something like this. But here, for simple RNN, let's keep it very simple. So let's return this thing into false and see what is the performance, right? So we talked about how we calculate these parameters as well in the intuition. Okay, so we can go ahead and create callbacks and optimizers. We do RMS prob. We can do Atom or RMS prob. It really doesn't matter for this simple data set. And yeah, we can look at the performance. The performance in the, obviously from run to run, these numbers are going to change, right? Because there's this random initialization for the weights of the neurons. Yeah, so here our simple RNN is doing a test MAE of 0.017. Remember, what was our benchmark? The benchmark test was 0.12. So we are doing a lot better than that. So we're doing a lot better than a forecaster. It is 0.017, right? So yeah, we can go ahead and plot the validation versus train. And yeah, this was our RNN. So remember this number, okay? Next, we're gonna use LSTM. So let's do LSTM for our airline passenger data. Again, remember this data is pre-processed. This is log difference of airline passenger. As you can see, the architecture is pretty much the same, right? So instead of using simple RNN, I just change it to LSTM and that's it. So that's why I wanted you to focus on the theory lectures a lot more when it comes to deep sequence model in general for deep learning, simply because the Python part is becoming easier and easier down the road. So you need to understand what is happening behind the scene. Okay, so this is our LSTM, and if you pay attention, the number of parameters of LSTM is exactly 4 times the number of parameters of RNN, right? Simply because we have 4 gates there, and for each of those gates, there's a set of weight, and that's why in this example, because we're using the same number of recurrent cells, this is going to be exactly 4 times your RNN parameters, right? So do I have it here? Yeah. So this is the number of parameters in the RNN. We need to multiply it by 4. That's what we get, 1152. Okay. So we can train this one as well. This should be also fast to train. And yeah. So, and then we look at the performance in the test set after the model has been trained. So let's give it some time. There you go. Okay, so yeah, this is performing exactly the same as, again, in this iteration that I'm running, the same as our RNN. So both of them are doing a decent job. Remember, this is a very simple, well-behaved data set. So yeah, this is our LSTM, and obviously when you're running it, you'll see a slightly different thing. Now we can go ahead and make the model more complex with regularization, right? So let's have fun. Let's add a bunch of extra layers and then have fun. So now I have simple RNN with 32 recurrent cells, and I'm gonna add another RNN on top of that with 32 recurrent cells. But now I need to make sure that for the first layer, the return sequence is equal to true. Because if you remember from the theory lecture, that's what we need to do, right? And yeah, then the rest is pretty straightforward. We have a bunch of callbacks, and then yeah, let's go ahead and run this. This is also pretty fast. And we are curious how does it, and I'm gonna let it run for 100 epochs. You can run it for longer. Again, because this is a tiny data set and you can afford to do that. All right, so as you can see, here's a problem, right? It seems that the validation loss is less than the train loss. So this is a clear sign that maybe your data set is not complex, your model is not complex enough, and we can even make it more complex, right? But again, here, this is just, I wanted to show you that how we can build up these models on top of each other and how we can have fun with that, right? So here the test MAE is even worse. It's 0.025. But again, the idea was that hopefully you could, by making it more complex, by adding some regularization, adding some dropout layers. So maybe this dropout was overkill here. So maybe we need to change it. Yeah, we talked about these dropouts in the theory lecture as well. So maybe here it was a little bit of overkill, so we are over regularizing it. That's why the validation loss is below the train loss. I could go ahead and make this one more complex. Instead of simple RNN, I can use LSTM on top of each other. I can do GRU on top of each other, and hopefully a good combination of complex model and at the same time regularized. It's going to help you to get a better performance, right? Yeah, but here we're keeping things simple and we just wanted to do a simple comparison. I can do bidirectional RNN. I don't expect it to perform better, but let's see how it does. Again, it's pretty straightforward. We just change the layers from simple RNN or LSTM to bidirectional, and we have to say inside that bidirectional, what kind of recurrent layer do you want? I say, let's do a simple RNN. And we can run this and see what we get. And let's see. Yeah, the same issue we have here. Again, the validation of the loss is lower than train loss. So we need to do something about this thing. In the train set, your model is not complex enough. Let's look at the performance. Yeah, it's 0.02. It's better than the LSTM here, but it's worse than our simple RNN. But again, this was just a coincidence, so don't read too much into these numbers here. Yeah, and I think at the end of the day, so these numbers are going to be different based on when you run these, especially the deep learning parts. But high level, we can make a fair comparison. Remember, I'm looking at this airline passenger data set. And I'm looking at a stationary data set, which is working with difference log passenger, right? If we do that, these are probably our numbers in terms of mean absolute error. The benchmark is 0.023 for seasonal naive forecaster. For naive forecaster, is 0.11. Again, these numbers might change. The econometric, it's doing a decent job. Our ARIMA did this, the ETS did this. Our machine learning throughout the semester, we looked into those numbers. This is what we got: 0.025, 0.028, and etc. And this is deep learning now, right? And as you can see, all of them are relatively performing the same. And this is the case here simply because we couldn't have a more well-behaved data set to work with, right? So what is the lesson learned here? If you have a simple data set, just go with your econometric model. Go with your classical traditional models, and they're going to shine. And if your data set is less well behaved and there are more complexity, more complex patterns in the time series, you can go ahead and try machine learning, deep learning on top of those things as well. Yeah, that was pretty much it. I hope you find it useful, and in the next video, I'll talk about the multivariate RNN and LSTM. So what we did here was just univariate. Remember, the number of features was only one, and that one feature was your time series itself. And the next one, we are going to do multivariate RNN and LSTM. Until next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.